showing up, it destroys the destructive interference. This is really big. The resulting expressions now are big enough that they can match with experiment. And also, because the up conversion and down conversion is composed of many excitation transfer steps, then this also applies directly to up conversion and down conversion for excess heat production. So this was a really, really interesting idea. Now the only thing that we need to figure out is whether the energy levels actually do shift off of resonance. So the question is, how big are these shifts off of resonance? So I decided to look at the deuteron as being the simplest problem that I could analyze. So I went ahead and said, let's go ahead and model the deuteron and include a correction due to, when the pion exchange happens, it notices whether you're on resonance or off resonance. If you're off resonance in one direction, the pion exchange gives a potential that's weaker and more limited. If you go in the other direction, it gets to be stronger and extends further. So this is the pion exchange in the case of a pseudo-scalar interaction. The pseudo-vector interaction for single pion exchange is going to work exactly the same way. So I can take, I took the Hamada-Johnson potential just because it was easy and I worked with it before. I added the off-resonant corrections to the central and tensor potentials. And here's what happened. So when you're on resonance right here, then there's no correction and the binding energy is 2.22 MeV. But if you go off resonance in one direction where you have more energy available, then the binding energy gets to be bigger and bigger and bigger. And these are gigantic corrections off of resonance. If you go the other way, the binding energy gets to be weaker. So what we learned from this exercise is that the off-resonant energy shifts are large, which is incredibly good for this approach in this model. In the case of the dineutron, which I can also model easily, I find that the dineutron is normally not bound on resonance. But if you go off of resonance by about 25 MeV, then the attraction becomes strong enough to make the dineutron bound. If you have neutron clusters, they would expect to bind with less energy off of resonance. And that provides a possible interpretation for the Imamura experiment. So if you start with palladium-110 and strontium-88, if you're producing excess heat, so you're putting palladium off of resonance, then you have the chance of having the neutron cluster be bound. If it transfers to the strontium, then you can make strontium with heavier mass, and it can go down a decay chain and turn into molybdenum. And this, of course, is testable. Current status, we now have an overall theoretical picture that addresses many problems. We now have some experimental support that the excitation transfer actually happens. In fact, at this point, I think we have a picture that is capable of doing the job and turning into a quantitative theory that could be used for modeling and simulation. To make it work, I need these two matrix elements, the D2 going to helium-4 and HG going to helium-3. Last summer I worked on this one. I have a poster on it where I can show you the details. It's quite the calculation. It's not quite done yet. I expect it to be done like within a month or so, hopefully, and then we'll have a number. This one, I have an earlier estimate for this, but I gotta do it and do a better job. I'm going to do iron 57. I'm going to do this for the Lipinski experiment and get some fun on nuclear exchange for low-level metastable states. On my wish list, I'd like to see experiments get to the bottom of this weak nuclear mission energetic particle emission effect. One example of it was by chambers, where if you assume that D2 goes to helium 4, you get 24 MeV and give it to a palladium nucleus and dig out an alpha, the alpha comes out with on the order of 20, 21 MeV, which is what Chambers saw. So we're going to try to do experiment something like this and see whether we can correlate the alpha energy or the product energy to the host lattice. Another thing on the wish list is this, that if we have excitation transfer and many steps, and if it's non-resonant, we pick up or lose some phonons each step. Well, if you take 100,000 steps, then you're going to get an energy spread on the order of 10 eV. And that's actually observable in a bent crystal spectrometer experiment. I'm hoping to move towards simulation models. I think I'm far enough along that we could actually begin developing simulation models that could be used to test or to compare against XSE experiments. And that's it. Thank you for your time.
Any question? Please start.